Yes, so we will go to this inception module. So this inception module, it was published in 2014 by a group of researchers at Google. And the main idea here was to build a deeper neural network while improving utilization of the computing resources inside the network using those inception module. So this is the classical CNN architecture. So it consists of, as you can see here in the top part, because I mean, I mean, why it's zoomed? Oh, sorry. So we will go to the inception part. Yes, so this is the inception part. So this is the classical CNN architecture. So it consists of, I mean, the top part, it is a classifier, dense classifier. We can call it dense classifier or fully connected layers. So this is the brain. In fact, this one, it is a brain, right? And this one, it's just, I mean, this feature extraction part, it works with the raw data, and it tries to extract some feature maps, right? Relevant feature maps. I mean, this one works fine, but if you want to improve computational, I mean, utilize computational resources in a much better way in your neural network, maybe you can try to test this inception modules. So we try to add here some inception modules, and it's one layer. In fact, it's inception module, it will be one layer. So this is, we call it inception module feature extraction. So by replacing some layers with the inception module, and we will see how it works. It's just an example, but maybe in some papers you will see many different, I mean, people are free to select how they want to design it. So the inception module is combination of 4 layers. First one, it's 1 times 1 convolutional layer, 1 times 1 convolutional layer, this one. And this one, 1 times 1, which means it has only 1 parameter, correct? So we apply, I mean, the filter size is 1 times 1, correct? We will apply it to the previous layer, the feature map from the previous layer, and we will get something else. As you can see here in this example, the feature map from the previous layer has a size of 32 times 32 times 200. And when we apply this 1 times 1 convolutional layer, it will not change the dimension. So the dimension will stay the same, 32 times 32. But what will change here? It's the depth, correct? So the depth here, it was 200. And when you use this convolutional layer, convolutional kernels 1 times 1, and 64 of this type, correct? It means we will convert the depth, it will reduce the depth of the feature map from 200 to 64. And this is very good. In fact, I mean, this 1 times 1, they call it bottleneck or dimensionality reduction layer, for example. And they use it, in fact, to enhance also to reduce computational resources, enhance the computational, I mean, capability or reduce number of operations. When we try to convert this one from 200 to 64, if you will send this one to the next layer, and if you need to, if it will be a conv layer, for example, so now we are reducing the dimension of the depth from 200 to 64. So should expect that number of parameters in the next layer, it will be much less. We will talk about it in the next slide anyway. So anyway, it will consist of a combination of 4 layers. The first layer will be 1 times 1 convolutions. The second one will be 3 times 3 convolution. When you apply this one to this one, it will convert with 128 filters. 128 filters with 0 padding, of course, right? So it will convert this one from this into this one. This is traditional 3 times 3 convolutions. 5 times 5 convolution, it's also the same, no problem, right? No change. But this one also, it will be the size of 5 times 5 with 0 padding, right? And it will be 32 of this one. And maybe the fourth layer, it will be 3 times 3 max pooling. When we apply this one, it will be 32 of this one, right? 3 times 3 max pooling. It will convert this one into this one. And at the end, I mean, this we will try to concatenate the outputs of those layers are concatenated into a single output volume, forming the input for the next stage. We will concatenate the depth. If you want to concatenate the depth of the 4 outputs, we need to be sure that the dimensions are the same. So as you can see, here's the dimension of the first one. The output from the first layer, it will be 32 times 32, the second. So the dimension is the same, in fact, right? So we will just concatenate the depth. So we will put this one, and after that, we will maybe add this one. So it will be 64 plus 128 plus 32. We will make it like this one. So the feature map from the first one, it will be like this. Correct? It will be something like this one. We will concatenate it with the second one, which is like this one. Correct? The fourth one, the third one, it will be like this one. And the fourth one, it will be like this one. Correct? We'll just concatenate it into one volume. This volume will be 32 times 32 times 256. So this is concatenation. So this is the inception. We call it inception module, and you will just try to add more of those inception modules in your model. So what is the function of this 1 times 1 convolutional layer? So the idea here is to add 1 times 1 convolutional layer before bigger kernels, like 3 times 3 and 5 times 5 convolutional layers to reduce their depth. It will just reduce the depth, which in turn will reduce number of operations. Because imagine that I have a volume which is a depth equal to 100, and I want to apply 3 times 3 to this one. So in fact, the size of the filter in this case, it will be 3 times 3 times 200, right? So number of calculations, number of multiplications will be much higher. If you can apply this bottleneck layer or 1 times 1 layer, for example, in this example, we have the input volume is 32 times 32 times 200. When we apply this 1 times 1 conv 16 filters of this one, it will reduce the dimension into 32 times 32 times 16, right? When you apply this 5 times 5 filters, so what will be the size now, or number of parameters, for example, if it will be 32 of this one. So if it's a 32 filters, we will get the depth will be 32, correct? But number of calculations will be, number of multiplications will be much less, number of parameters will be much less, correct? Because here's the filter size will be 5 times 5 times the depth, which is 16. How many of those? 32, correct? Plus, of course, 32. This is number of parameters plus 32. It will be like this one. But if I want to apply this one directly to the input volume, is this 5 times 5? So it will be 5. The size will be 5 times 5 times the depth of the original input, which is 200. Correct? Multiplied by how many filters? 32 plus 32. So just compare. Just make comparison between those two numbers, right? So when we use this bottleneck layer or dimensionality reduction layer or reducer layer, it will reduce the depth of the input volume from 200 to 16, correct? And you can just imagine, how much reduction, number of parameters will be much less, number of weights will be much less, so the model, the chances to overfit will be much less. In this case also, we need less number of the data set size will be less. The required data set size will be much less because number of parameters will be much, much less. So if we need to calculate the computational cost, which is just the number of multiplications, right? This computational cost. When I need to apply this bottleneck map reducer to this input volume, so the computational cost will be like this one. Just number of multiplications. So it will be, I need to get this number, so it will be 1 times 1, right? 1 times 1 times 200, correct? This is my filter, multiplied by 16, correct? Multiplied by 32 times 32, because this is number of multiplication, because I will apply this filter to each pixel value. So the computational cost will be 3.2 million. If you need to apply this conv layer to this bottleneck, the output from this bottleneck, the computational cost will be 13.1 million. So in total, it will be 16.3 million. If I need to apply this 5 times 5 times 32 directly to the input volume, which is 32 times 32 times 200, it will require this number of operations. Can you imagine? So now we can go down from 163 million to 16.3 million. I mean, it's a reduction by maybe more than 90%, correct? So this reduction, it's more than 90%. So this bottleneck layer or reducer layer or dimensional reduction layer, it will help us, in fact, to enhance the computational resources, to utilize computational resources in the best way for training our model. So the conv layer or reducer layer, the idea here is to it preserves the spatial dimension. It does not touch the spatial dimensions, which is height and width. It will just work in the depth, right? It changes only the number of channels of the input volume. So when I apply this one to this one, I mean the depth here, it's a 32. I apply 1 times 1 to this one here. We will apply we will apply this filter to the first pixel, and we will go to the second pixel, and so on. So in fact, the output dimension will be the same as the input dimension in terms of the dimension. So we will have 6 times 6 height and width will be the same, but the depth here will change. So for example, if you decided that how many filters here, right? So the size of this one, in fact, it will be 1 times 1 times 32, because the depth here, it's a 32, correct? Multiplied by the number of filters. If you want to reduce this one from 32 to 6, so number of filters will be 6. So now this one will be multiplied by 6 plus 6. This one will be a number of parameters. When I apply this one to this volume, right, it will generate only 1 pixel value. It will generate the first one. But I need to apply it 6 times. So this one will be 1 time, this one will be another time, 3rd, 4th, 5th, and 6th, for example. So 1 times 1 conv layer, it preserves the spatial dimension, but it changes the depth. And when we change the depth, we will not change the inception field, but we will reduce number of parameters, the number of calculations, or number of multiplications, right? So in the inception module with dimensional, we can adjust them. We can modify the inception module and add some dimensional reduction to it. So just adding 1 dimensional reduction to each layer, for example. So it will be like this one, right? Sorry, yes, 1 conv. So it will make also, and after that we will do this depth concatenation, for example. So GoogleNet architecture, which uses this inception modules. So this is the structure of it. The top part, it's the classifier part. And the top part, it consists of 2 fully connected layers. We have here 1 fully connected layer followed by softmax layer. And this is the feature extraction part. This is the feature extraction part. So the feature extraction part, it consists of a conv layer followed by max pooling, conv, max pooling, and after that inception, followed by max pooling, inception, max pooling, inception, global average pooling, right? So just build this inception module and try to build your model like this one, right? So this is Google LeNet. That part, it's identical to AlexNet and LeNet, which contains a series of convolutional and max pooling layers. This is very traditional, but part B here, it's different because it contains the 9 inception blocks and separated 3 by 3 max pooling layers. So this is a different part. And of course, the classifier, this is a traditional part which we have. Now I need to use this inception or Google LeNet to just transfer it to another problem, for example. So I will try to use it for CFAR10. So I will define my model as a sequential using sequential API. I will import inception v3, right, as a layer, just to import it as a layer. So I imported it as a layer now. Weights are obtained from training the model on ImageNet, right? Include top part false, because I don't need to keep this top part. So include top equal false, right? Include top equal false. The input shape, it's 75 times 75 times 3, which is the size of the CFAR10, right? We will flatten, the output from this is the feature extraction, correct? Layer. So this is the feature extraction layer, but it's compacted. We will flatten the output from this one. And now I will define my classifier because I removed the original classifier and I will add my own classifier. So it will consist of three fully connected layers. The fully connected layer, first fully connected layer has 1024 units. Activation layer is ReLU. I will use dropout because maybe chances to overfit will be high. So I use here dropout with 0.5 dropout rate or threshold. The second dense layer has 128, uses RELU, and the output layer, it will be 10 units, and the activation layer will be softmax. So usually they call it softmax layer. I mean, this is model summary. You will get this table. This is a number. I mean, remember also model.layer 0 trainable equal false. So this is very important because we will freeze the model of the feature extraction part. This one, it will freeze those parameters. So now from this one, the parameters of the inception module, it's this large number. Can you read it? Yes, it's 21,802,784. So it's 22 million parameters, and it's frozen. So this one will be non-trainable, correct? This number will be non-trainable. So flatten does not have any parameters. The first fully connected layer has this number, right? If you want to get this number, it will be multiplication of this number by this number plus this one. Dropout, it does not have any parameters. The second fully connected layer, it has 128 units. So number of parameters here, it will be 128 multiplied by this number plus 128. And finally, we have the softmax layer to classify each image into one of 10 classes. We will train the model, and for 50, we train the model for 50 above. And as you can see here, this is a training loss and validation loss. Maybe I was expecting here to see also training and validation accuracy, but I didn't print it. Maybe I didn't. But you can go to the code here and check it, right? And this is the confusion matrix. In this CFAR 10, CFAR, we have 10 classes as well. So this is the confusion matrix. Maybe it was also nice if you can try to get if you want to score precision, recall, accuracy. I don't have here accuracy. Maybe you can get also the classification report, if you can remember, because the classification report, it will give you all numbers in one shot. So you can have the precision recall for each category or for each class, not only overall, but maybe you need to get it for each class, because maybe the model is very clever in classifying some classes, but not all classes, right? So you can get all those details when you try to get out this classification report. Yes, so this is Google LeNet, right? We have something called also, this is the last one, which is ResNet, which is Residual Neural Network. ResNet was developed in 2015 by a group from Microsoft research team, and they introduced novel residual module architecture with the skip connection. We have here for the first time something called the skip connection, right? Skip connections are shortcuts that allow the gradient to be directly backpropagated from earlier layers to be to later layers, right? We have here earlier. I mean, we have earlier layers, which means we are close to the data, right? Raw data. We have here data or input. So it will try to propagate the gradient directly to the from later layers to from earlier layers to later layers, creating an alternative shortcut path for the gradient to flow through, solving the vanishing gradient problem. It's a way for improving learning by trying to minimizing this vanishing gradient problem, which is another important benefit of the skip connection, is that they allow the model to learn an identity function, which ensures that the layer will perform at least as well as the previous layer. When you try to use this skip connection and they propagate the gradient from those earlier layers to the later layers, in fact, you provide all information to the later layers to train and to perform at the same performance of the earlier layers, which is close to the input, right? As you know, I mean, yes, skip connection plus main base. I mean, this is the skip connection in traditional neural network. Without this is shortcut path or skip connection. Convolution layers are stacked one after each other. In case of ResNet, we will stack convolutional layers as before, but we will also add original input to the output of the convolutional block. So we will just have this shortcut, and we will try to propagate this input to later layers. And here it will be concatenating, right? So this is, I mean, this is the traditional approach, main path. We have some input X, we will apply conv to X, and we will apply RELU to the output from this conv. And after that, we will apply another conv, for example. So we will get f of X here, right? So we will have this concatenation here. We will concatenate fx with x, correct? So this is how escape connection works. And after that, apply RELU to the output from this escape connection. So you can just say if you want to implement it maybe quickly, for example, x shortcut equal x, for example, and the output from the conv, it will be conv 2D, for example. Filters, the number of filters, the kernel size, stride. The input is x, and when the input is x, we will get something here, right? We will call it x also, and after that, you will apply this x to the activation function. You will get another x here, and you will apply this x to this conv layer. You will get another x here, and at the end, you will just concatenate x with x shortcut. So we will add the output from this one with this one, right? And we will send it to the next RELU or the next layer, right? The building blocks. So ResNet is composed of a series of these residual building blocks that are stacked on top of each other. This is the classical approach. We have input, we have conv layers followed by pooling layers, conv followed by pooling, classification or classifier, which is a number of fully connected layers. This is the inception module. We just replace or just add those inception modules, right? And that is it. For the residual block, we will add some residual blocks, correct? And this is how it looks like this residual block. For example, so this is X. We have conv 2D, batch normalization. We described the batch normalization last time. RELU batch normalization is very important because it will enhance learning also. RELU, conv, batch normalization, RELU. So you will have those skip, you call it skip blocks or skip residual blocks, sorry. We call it it's residual blocks. Yes, ResNet 50, if you need to implement this residual neural network, ResNet 50, which consists of 50 layers. This one consists of 50 layers. And also it's, if you want to use it in Keras, for example, so you need to define a model as a sequential, using sequential API, add ResNet as a layer to make your code is compacted. So I'm just adding here ResNet 50 as a layer. Weights are imported from ImageNet, include top equal false. The input shape will be this one. So in this case, maybe we will use it for this fashion data set, for example. You will flatten, you will get feature maps from this one, flatten it, and add your classifier. Your classifier here, it will consist of 3 fully connected layers. The first one has 1024, dropout, 128, and 10 softmax, right? And of course, model.layers 0, trainable equal false, because I don't want to I want to freeze the parameters or the weights of the, I don't want to retrain it. So now when we retrain the whole model, we will train only the classification part, not the ResNet part. Yes, so now I'm training the model for 40 epoch. This is the model summary. So this is number of parameters, which is non-trainable, correct? And this is the output shape from this is the feature map. It will be like this one. It will be 1 times 1 times 20, 48, right? Flatten it, so it will be this one. So this one was like this one, 1 pixel, and the length was like this one, correct? So it's 1 times 1 times 20, 48, right? So just convert it into one vector, correct? Maybe we don't need flatten here, in fact, but anyway, we converted it into this vector using a flatten, and we will send this input to the first dense layer, which has 1024 parameters, the dropout, right? The second 128, 10, and so on. So, and finally, we have this kind of confusion matrix. Yes, so we just finished that part. So please, if you have any questions, we are finishing now. I just want to, do you have any questions first? Yes, so in fact, I just want to check. Check what has been done this semester. If you can see my screen here, right? We have been working this semester with, we have in Blackboard 9 sections. I call it week 9, from 1 to 9, for example. So in the first week, we talk about, you do HPC something. We have some lecture 1 introduction, right? Lecture 2, it was types of machine learning. Lecture number 1, it was advanced machine, and it's just the introduction to the course. In week number 2, we covered many things, in fact. It was perceptron and perceptron learning rule, if you can remember. And we covered lots of stuff in this slide. In week number 3, we covered this confidence interval. We covered STK-learn, introduction to STK-learn. In week number 4, we covered ensemble learning, introduction to ensemble learning. Again, confidence interval, data pre-processing, right? Number 5, we'll talk about F1 score. We'll talk about pipelining in STK-learn. It was, important because it will make our work more organized. It's a good habit if you can stick to it. And the synthetic 2 moons dataset, it's just one dataset which we have been playing with. We talk also about working with unlabeled data, correct, when it's unsupervised. In week number 6, we have been talking about fundamentals of deep learning, CNN, practical examples. In week number 7, or group number 7, we'll talk about more about convolutional neural network, ConvNets. Advanced CNN, we covered it today, in fact, right? So it was from this week 7. And week 8, we talk about recurrent neural network, right? We have been doing very nice stuff here in this RNN. And we use RNN for different applications. We have been working with text data, right? Time series data. We had lots of examples in this RNN. I guess it's very important for people who want to use recurrent neural network in their work. And finally, week number 9, we'll talk about batch normalization and one-shot learning, right? Batch normalization, it's very, very important, and one-shot learning. So in this case, we finished this semester. So please let me know if you have any questions, and if you have any suggestion for next year, for example. So what should we cover next year, for example, if we need to update the course content? So if you have any suggestion, please send it to me by email, or just let us discuss it. It would be very useful. And yes,
Professor,
please.
I already sent an email with these questions to collect feedbacks from other students of the group, other students of this course, if they have any opinion and feedback for this particular.
Yes, please.
So if they can reply me, maybe I can compile them on all in one, and I can send it to you.
Okay, please. But anyway, I need to get a report from you.
Yes, I know.
Yes, because it's very important, because the faculty are asking about it. Please. So because we are supposed to deliver 2 reports, one in the middle and one at the end. So if you can send me the report which you have at the moment, and maybe after the exam we can get another report, it will be very good. And if you have any questions, any suggestion, please send it to me. And next week we will be off because I have a workshop in Rwanda, so we will be there for 3 days discussing a project. So next week we will just take it off, and maybe the week after we can just have some optional. If you want to present your results, it's optional. So we will have, if you want to get some feedback, for example, if you want to present your work and if you want to get feedback, just try to join us, please. After 2 weeks, it will be also Friday, not next Friday, but Friday after next Friday. We will have also from 9 maybe to 12 or more, and you can just present some results. For example, maybe you can just use 10 minutes for presenting your main results, and it's optional. So, if you have something else, or if you want to send me your report, for example, by email, and I can give you feedback by email, it's fine. But it would be nice if you can present your work after 2 weeks from now, some results, for example, so we can try to discuss it and try to give you some feedback. And for the exam, we extended it to, I put message in Blackboard, so it will be 8th of June. So you can submit your report starting, I guess, from 5th to 8th until noon, 8th of June. There are some cases who want to get more extension, some individual cases. And those individual cases, they will get also some individual extension, because some people, they got sick, for example, or they have any conditions. So those special cases, they will get individual extension. But the main deadline for our course, it will be 8th of June. For the report, just try to submit something which can be reused later on, right? So my idea here is to try to write your report as a paper, for example, It could be a conference paper in a conference paper format, for example. So after the exam, you can try to proofread it and you can try to publish it. For example, it could be one publication in your PhD. It would be nice. So try to submit your report as, for example, like conference paper in IEEE format, for example, and it should contain something which can be published results. So try to select a nice title, try to write nice abstract, good introduction, right, with some literature review, maybe materials and the methods, your results, concluding remarks, summary, for example. So it should contain the main parts of an article. I don't care about the size. The most important is the value and the content. So it could be like 6 pages, for example, in total, or 8 pages. It will be fine. But to try to add some results which can be published later on. Yes. So any questions, please? Do you have any questions? So please, do you have any comment on the course, how we organize it? If there is something which we can make better, for example?
Can we send that to you by email later?
Presentations?
No, just like kind of a review and like comments that we have or things that could be improved.
Yes, sure. Yes, please. Yes. Yes, send it by email, please. So, but in general, the course was okay this year. I mean, this year I got sick, unfortunately. So I have been away for maybe 2-3 weeks. So things maybe was not very organized this semester, but I tried to do it as best as I can. And we updated the contents a little bit this time. We added maybe some other parts which has not been there last year. But maybe also next year, maybe we need to update contents. Maybe we need to add more state-of-the-art models, for example, and approaches. So if you have any comments, please try to send it to me so I can have it in my notes and I can work on it for next semester or next year. And thank you very much for joining this course and enjoy, the rest of the course. If you have any questions, just contact me and I try to work on your course report. It's not for the course. It's just a publication which can be counted in your PhD work, for example. Just to try to write something which will require less work from you after summer, for example, or in summertime. So just submit it to me in Spera, and after that, try to maybe proofread it, try to readjust, and maybe send it to a journal or a conference. It could be, last year, for example, we have many people who published journals and conference papers after the course from this course report. So try to have this mindset. It's not for the exam, but it's just for your PhD. Try to write something which can be published. So at the same time, you can pass the course, and at the same time, you can get one publication point. Yes. And please, if you like the course, try to maybe write recommendations in my LinkedIn account. I will put it in Blackboard. So if you feel that it was useful for you, maybe you can write something on my LinkedIn to recommend the course to other people. Yes. So I guess we are at the end of the course. So please, just if you want to say something.
Yeah. Thank you for the course.
Thank you very much. Thanks. Just please contact me if you have any questions, even after the course. So even next semester, for example, if you are working in something where I can help you, don't hesitate, please, to contact me.